Hello everyone. In this chapter, which is chapter number 37 of your book, we are studying about hard disk drives. If you remember, in the last chapter, we studied about I/O devices and how a general or a typical I/O device works and how does it communicate with the system, computing system. In this chapter, we are going to focus and get to a specific type of I/O device, which is the hard disk. Okay, so hard disk, from the point of view of the CPU, is also an input-output device. Okay, so it will communicate with the hard disk just like it would communicate with a normal I/O device. So, what does a typical hard disk look like, and how does it function internally? We'll study in this chapter. So, hard disks, as you know, traditionally, we have the hard disks which had rotating components inside them. So this is the kind of hard disk that we will study in this chapter. Now there are like some very expensive hard disks which are flash based and which we call SSDs or solid state drives, and they do not have moving parts in them. Okay, so we will not study those solid state devices, SSDs, but rather the typical hard disk which had moving parts inside them. And that's because even now more than 90% of the hard disks are based on rotating devices. So let us see what is a hard disk and how does it work. So hard disk is an I/O device and it is used for persistent storage. Okay, so persistent storage, if you you must know, is the non-volatile storage. Okay, so in computers we have two types of storages: volatile, which are temporary storages, and non-volatile storages. So hard is one of the examples of non-volatile storages. Okay, so non-volatile storages, we call them persistent storages also. So this basically means if a data is written to the hard disk, it will stay on the hard disk and will be preserved even if there is no power to the system. Okay, so even in a case of loss of power, the persistent storage will retain its data. Okay. While compared to it, a non-volatile storage, a volatile storage like RAM would lose its data if there was a power loss. So internally, the unit of storage of hard disk is a sector, okay? And each sector is typically 512 bytes large. Okay? So unit of storage means if a data is written or read from the hard disk, it will always be in a multiple of sectors. We cannot read and write 1 byte to the hard disk. If you want to read 1 byte, you will have to read that whole sector, and from within that sector, you will read the value of the byte in which you are interested. Okay, so hard disk read and write happen at the granularity of sectors. Okay, we cannot write data less than a sector to a hard disk. And sectors in hard disk are numbered from 0 to n-1. Just like bytes in RAM are numbered from 0 to n-1, in hard disk we have sectors that are numbered from 0 to n-1. The hard disk manufacturer guarantee us that writes to a sector are atomic, okay? Which means when I/O is done on the hard disk, it is done in units of sectors, and reading data from one sector or writing data to one sector is atomic, which means when we write data to one sector, it will either be written whole, the operation will complete, or it will not happen at all. It will not happen that our write gets interrupted in the middle and half of the sector is written and half of the sector is still not written. Okay? So it will be performed atomically. Either the whole sector will be written or none will be written at all. Okay, so writes to the sectors are atomic. So we can have writes which are bigger than one sector, like your very huge write where you are writing a lot of data to the hard disk, but it will be divided into sectors. Okay, so that write will be divided into 5 and 2 byte portions, and each portion will be written to a sector. Okay, so bigger than the sector writes, it is possible that they get interrupted in the middle, and half of that write is done and half of that write is not done. Okay, so, but if the write is to a sector, that is atomic. It will either be written completely or not written at all. Secondly, due to the structure and geometry of the hard disk, accessing blocks which are near to each other is faster when compared to blocks which are farther from each other. Okay? So for this chapter, you can use the term sector and block interchangeably, but later we'll see that the actual hardware division of a hard disk is in sectors, but the operating system views hard disk in terms of blocks. Okay, so blocks is at a higher level, a division of hard disk, where a hard disk is considered to be a contiguous array of blocks, okay? And the size of a block can differ from the size of a sector. But that's the logical view by the operating system of the hard disk. Actually, in reality, the hard disk is composed of sectors. So that's basically some basic info about what is a hard disk or what comprises a hard disk. If you go into further detail, then let us discuss the physical geometry of a hard disk. Okay? So a hard disk is composed of different platters. A platter is a metallic plate, a circular metallic plate, which is made of some metal, for example, aluminium, and it is coated with magnetic material on both sides. Okay, so a platter is a circular metallic plate coated on both sides by magnetic material, and that magnetic material is basically used to store data. Okay, so we use the magnetic properties of that material to store different bits inside that material, and once we have basically written data to that magnetic material, it will keep its shape or its internal structure to store that data even when there is no power. So both sides of the platter are used to store data, and a hard disk can have one or more platters. Okay, so they are arranged vertically on top of each other if there are more than one platters. So a side of a platter is called surface, and as I said, both sides of a platter are used to store data, so both surfaces are used to store data. And if there are more than one platters, they are placed on top of it, and through them, from this through their center passes a metallic rod which you call spindle, which is basically used to bind those platters together. And this spindle can rotate, and these platters, they rotate with this spindle. And the rotation of this, the speed of rotation of this spindle or these platters is given in revolutions per minute. Okay, so when you take your hard disk at the back, you will find its speed in RPMs or revolutions per minute. You have hard disks that have like 5,400 RPM or 7,200 RPM or 15,000 RPM. So there are different speeds of different hard disks. They are basically, this is the speed of the rotation of the platters. So on a surface of a platter, on one side of a platter, you have basically concentric circles. Okay? And these concentric circles, one inside another and outside another, these circles are called tracks. Okay? And these tracks are composed of sectors. Okay, so sectors, as we discussed, is a unit of storage of hard disk, and one sector is usually 512 bytes. Okay, so data is stored in these sectors. These sectors are arranged in a circular fashion, and each circle made up of many sectors is called a track, and there are many tracks, many concentric tracks on one surface or one side of a platter. Okay? And disk head is a device which is used to read or write data on this tracks, sectors, or surface, whatever you call it. So this material, magnetic material, is manipulated by this device, which is called disk head. Okay, so disk head moves on the surface of a platter, and it moves between different tracks and different sectors, and it can write data on in that magnetic material. And this head is moved by a mechanical device called a magnetic arm. So this head is attached to a magnetic arm, and basically the arm moves the head across different tracks on a platter surface. So let's look at a simplified example. Here we have the top view of one surface or one side of a platter. This is a platter, and it is attached to this spindle. Okay. So for simplicity, this track has only this surface has only one track. Okay. This surface has only one track, which is this circle, and this circle is made up of different sectors. Okay, so here you see different sectors named from 0 to 11. This track has 12 sectors, and this is the head, which will basically read or write data on the surface, and this head is attached to this arm. Okay. So this arm is used to move this head across the platter. We'll see on the next slide. So in this figure, this head is resting on sector number 6. Okay, so right now it can perform operations, read and write data to and from this sector number 6. Okay. If we want to read data from another sector on the same track, then we'll have to rotate this disk. Okay, remember, the spindle can rotate these platters. So spindle will rotate this platter, and it will rotate it sufficiently enough that the desired sector is under the head. Only then the head can read and write data from that sector. Okay. So let's say if this after sector number 6 we want to read or write data to sector number 10, then we'll have to rotate this surface or this platter in this anti-clockwise direction, so that sector number 10 basically comes under this head. So sector number 10 will move from here to here, and then we can read and write data from sector number 10. Okay. And from the description of your book, it seems that the hard disk platters, they rotate only in one direction, which is anti-clockwise direction. Okay. So if we want to read data from sector number 5, then we'll have to give it a full rotation, so that sector number 5 rotates and it comes here under the head. Okay. Only then we'll be able to read or write data from sector number 5. So if you want to read or write data from different sectors, then there is this rotational delay. Okay, so the time that it takes us to rotate the platter so that our desired sector comes under the head. Okay, and this rotational delay is a mechanical delay, which means this is mechanical movement, and mechanical movements are very, very slow compared to electrical signal propagation. Okay, so this is why in rotating hard disks, most of these delays, they come from mechanical movement, and one of the mechanical movement is this rotational delay. Okay, so that is why after sector number 6, reading or writing data from sector number 7 will be much quicker than reading or writing data from sector number 0, for example. Okay, because the rotation delay for after sector number 6, reading or writing from sector number 7, the rotation delay will be much less compared to the rotation delay we'll have to suffer to read or write from sector number 0 after sector number 6. Okay, so keep this in mind that most of the delays in hard disk come from mechanical movements, and one of the mechanical movements is this rotational delay, and rotational delay basically is lower for adjacent or close sectors which are close by on the same track compared to sectors which are far away on the same track. Okay. So again, to read from sector number 0, we'll have to do half a rotation at least. And what's the max rotational delay? So max rotational delay will be a full rotation. For example, if after sector number 6, we want to read from sector number 5. Okay, so we'll have to do a full rotation. So on average, we get the average rotational delay for hard disks, and average rotational delay is basically half the full rotational delay, because sometimes we'll be reading from sectors which are nearby, and sometimes we'll be reading from sectors which are far away. Okay, so on average, we'll be making like half a rotation for every read. So here we have like another platter which is slightly more realistic, that instead of having one track, we have multiple tracks. Okay, so if we, in the last slide we discussed that if you wanted to read data from the same track, then we have to rotate the hard disk so that the desired sector comes under the head. What if we want to read data from a different track? Okay, so in that case, we will have to move this head across the tracks. Okay, and this movement is done by this arm. Okay, so this arm to which this head is attached, it can move left or right. So in this way, it can traverse different tracks on the surface to get to the right track. Okay, so this movement of the arm to get to the right track, we call it seek movement. Okay, so as we discussed, most of the hard disk delays come from mechanical movements, and these mechanical movements usually comprise of the rotational delay and the seek delay. Okay, so to get to a desired sector, first we get to the desired track by using this arm or seek movement, and then once we are on the right track, we rotate the hard disk to get the desired sector under the head, and this movement is the rotational delay. Okay, so rotational delay and seek delay basically are the main delays in reading and writing from hard disk. Okay, and these delays are much higher than electrical signal propagation delay. So seek movement, this movement seek, it can be further divided into different phases. Okay, so the arm is static, it starts moving, so there is some acceleration. So the first phase we call it acceleration, and then after accelerating it reaches a top speed, and after reaching a top speed it will continue to move on that top speed. We call this movement as coasting, and then ultimately it will start nearing the desired sector, desired track, and it will be start slowing its speed. So this slowing of speed we call it deceleration, and ultimately it will basically arrive on the desired track and settle at the appropriate position on that track, and this last phase of movement is called settling. Okay, so this seek movement basically it is further divided into these four sub steps. Okay, acceleration, coasting, deceleration, and settling. So seek time again, as I said, is this time moving from one track to another, and this is one of the major delays in accessing data on the hard disk. So your I/O time, the total time it takes to do an I/O on the hard disk, will be composed of the seek time to get on the right track, and then the rotate time once on the right track to get to the right sector, and then once you're on the right sector, then you will do the transfer. Okay, and I hope by now you realize that the seek time and rotate time are much larger than transfer times. Okay, because transfer is electric signal propagation, while rotation and seek are mechanical movements. Okay, so they dominate the I/O times for most of the I/Os, especially for small I/Os. These two times completely dominate the I/O time. The transfer time is negligible compared to these two times for small I/Os. So since this movement is slower and it takes time to get from one sector to another, to facilitate read and writes which cross boundaries of a track. Okay. So let's say you have this read request which comprises of this sector number 22, 23 and 24. Okay, so as you can see, this read request will have to cross the track boundary to move to another track to basically read these three sectors 22, 23 and 24. So as you can see, the 22, 23 they end here on this track, on the middle track, and 24 it does not start immediately after 23. So this is sector number 23. This is sector number 23. After 23, reading from 23, 24 does not start immediately on the next track right here. Okay. 24 is slightly skewed after a certain delay. 24 starts. This is sector number 24. Okay, so what happens is that when the disk is reading from 22 and then 23, the platter is rotating. Okay. The platter is already rotating, and now the arm has to move from this sector, like this track, middle track to the inner track. So this seek movement, it will take some time. Okay? It will take some time, and since the disk is already rotating, then by the time this arm arrives here on this inner track, if sector 24 was here, it would already have passed under the head. It would have passed under the head, and we'll have to make a full rotation to bring this 24 under the head here. Okay? So for this purpose, hard disk manufacturers, they do this optimization and arrange the tracks in such a way that the sectors that cross track boundaries, the next sector like 23 ends here, and 24, instead of starting here on the inner track, 24 starts a little skewed. Okay? So these tracks are a little skewed. So 24 starts after this distance. Okay? So this is so that after reading 23, when the disk is already rotating, the head moves from middle track to inner track, and the time it takes for the head, the seek time it takes for the head to move from middle track to inner track, by this time, since the disk was already rotating, this sector 24 will have arrived under this head. So all these calculations, it has already been done by the disk manufacturer, and they have, according to their seek delays, they arrange their sectors in such a way that when the arm starts moving from here to middle track to the inner track, the rotation of the disk is such that the sector number 24 is placed at such a distance that by the time the arm arrives here, sector 24 would have moved under the head. Okay? And the head can now continue reading from sector number 24 after this sector number 23. Okay? So this track skew is basically to facilitate transfers which cross track boundaries. Okay? This is an optimization that the hardware manufacturers or the hard disk manufacturers do internally. Then also, since this seek movement and rotate movement are very slow, most hard disks, they come with a cache. Okay, so you know the principle of a cache, that the principle of a cache is to store frequently accessed data or data which will be accessed in near future. We store it in a fast memory. Okay? So while hard disks are very large, they can have some small amount of storage which is like non-rotational based and which is very fast, but its size is very small. So let's say if we request a if we receive a the hard disk receives a request to read from sector number 2. So it will read from sector number 2, and what the hard disk will do is that it will bring sector number 2 in this cache, which we call track buffer, and also sector number 3, it will bring it in this track buffer. Okay, so this is because if somebody is reading sector number 2, then most probably they will also be needing to read sector number 3. Okay, so in advance we bring sector number 3 in the cache, so that next time when the request comes from sector number for sector number 3, we don't have to do that rotational delay, and we can read directly from the cache for sector number 3. And secondly, if somebody has requested sector number 2 right now, most probably they will also request sector number 2 again. So for that, we do not need to go and read sector number 2 again from the platter, but rather sector number 2 has been brought into the cache, and we can read next time they request sector number 2, we can read sector number 2 directly from the cache, and we do not to go and read from the platter. Okay, so this will basically make those frequently accessed requests much faster. Okay, because this part of the hard disk, which is non-rotation based, it will be much more faster than compared to this rotational hard disk. Okay, so this cache within the hard disk, it is called track buffer. Okay, so track buffer keeps the frequently accessed or frequently accessed sector or sectors which it thinks which will be accessed in near future inside the cache. So when you have a cache, then writing can be done in two ways. Okay? When the operating system or the CPU tells hard disk to write XYZ data into the hard disk, then the hard disk can send a completion signal that the data has been written in two ways. One is that which is called write back method. In this method, the hard disk, the data that is to be written in the hard disk is first written in the cache, and once it is written in the cache, then we can send the signal to the operating system that it's okay, data has been written on the hard disk. Data has not actually been written on the hard disk, it has only been written in the cache. Okay? So in write back method, we store the data in cache and send the completion request to the hard disk, the OS. Okay? And later we continue to transfer this data from the cache to the actual sector on the hard disk. Okay? So this is one strategy of signaling write completion when we have a cache, and the other strategy is that as well as writing data in the hard disk, we also write this data on the platter in the sector on the actual hard disk, and only after the data has been written in the hard disk, we send a completion request, completion signal to the OS. Okay? So you can basically see the advantages and disadvantages of both these strategies. In first write back, completion signal is sent as soon as data is written in the cache. Okay, so the advantage is that writes are much quicker in this write back cache. Okay? While in write through cache, completion signal is sent only after the data has been written in the sector on the actual plate. Okay, so it will be much slower to send the completion signal on hard disk in a write through strategy. Okay, so the advantage of write back is that completion signal is sent much quicker compared to write through. But the disadvantage of write back cache is that it does not give the actual picture to the OS. Okay, so it is possible and there is a risk that data has been written in the cache, it has not yet been written in the hard disk, and the write back strategy sends the completion signal to the OS, and let's say we have power failure. Okay? Since OS has received the completion signal, so the OS basically thinks that data has already been written to the hard disk. But due to the power failure, data was not, the hard disk was not able to transfer data from the cache to the actual platter or actual sector. Okay? So this kind of problems can happen in the write back cache where the OS thinks that the data has been written to the hard disk while data has not been yet written to the hard disk. So this kind of inconsistencies can happen in the write back strategy. Okay, so for a hard disk that employs this write back strategy, it has to take into account the occurrence of this kind of inconsistencies, and whenever there is a reboot or power is restored next time, it should detect this inconsistency and take care to basically cover it up, okay, to make the hard disk consistent. So here are basically the two strategies of writing when you have a cache in your hard disk. So now let us see two concrete examples. We have two hard disks, and on the back of every hard disk you will see this kind of information given to you about different characteristics of the hard disk. So we have two hard disks, one is this Cheetah and the other is this Barracuda. So capacity, this hard disk is 300 gigabytes and Barracuda, this one is 1 terabyte. Okay, so it's much more in capacity compared to this Cheetah. In terms of RPM, revolutions per minute, basically this the rotation speed of this hard disk is 15,000 RPMs, and for this we have 7,200 RPM. Okay? So based on this rotation speed, we will calculate the average rotational delay for each hard disk. Okay, so remember, average rotation delay is basically half of the full rotation, the time it takes to do half rotation of the platter. Again, the average seek time, the manufacturer also provides you the average seek time. Okay, so average seek time for this one is 4 milliseconds and for this one is 9 milliseconds. And it also gives you the max transfer rate. The max transfer rate for this one is 125 megabyte per second, and for this one it is 105 megabytes per second. Okay, so max transfer rate basically tells you that once the head is in position after rotation and seek and the transfer starts, at which speed data can be sent or received from the hard disk. It gives information about number of platters and the size of cache on both hard disks and the type of connector. Okay. So if we have these two hard disks with these two specifications, what can we conclude about their transfer rates? So the time it takes to do the I/O, as we have already discussed, on each of these hard disks will composed of the seek time plus the rotation time, and once after seek and rotation the head is in position, the time it takes to transfer the data from the hard disk to the CPU, okay, or in the other direction. Okay. So these three times, seek time plus rotation time plus transfer time, they will determine the total time of each I/O operation. So the rate of I/O is basically the size of the transfer, the amount of data that you want to transfer, divided by this time it takes to make this transfer. It will give you the rate of I/O for each I/O operation. So on Cheetah, the average seek time was given to us 4 milliseconds. The rotation time, average rotation time we calculated from the RPM given to us, it's 2 milliseconds, and the transfer time is like 30 microseconds. Okay, so transfer time depends on the amount of data that you are going to transfer. So in this case, I think that amount of data in the example that is cited in the book, they are transferring 4 kilobyte of data. Okay, so 4 kilobyte of data, it takes 30 microseconds to transfer, okay, on this Cheetah hard disk. So I/O time total is like 6 milliseconds approximately, and which, as you can see, for small I/Os, the I/O time is totally dominated by these mechanical delays, which is the seek time and the rotation time. Okay. Actual transfer time is very, very negligible, 30 microseconds compared to 6 milliseconds, okay, on small I/Os. So on small I/Os, it is the thing to note that transfer time, I/O transfer time is totally dominated by mechanical movements of seek and rotation. Okay, so the total I/O time is approximately 6 milliseconds, and the rate of I/O, if we calculated the transfer size divided by time it took for that transfer, it will give you the rate of I/O for that transfer. Okay, so if it was 4 kilobyte transfer, we divide by 6 milliseconds, it gives us the 0.66 MB per second of transfer rate for this particular transfer. For Barracuda, we basically calculated the same specs using the same methods, and it gives us a transfer time of 13.2 milliseconds. Okay, so the same amount of transfer, it gives us basically a transfer rate of 0.31 megabyte per second. Okay, so see their advertised transfer rates here, 125 megabyte per second and 105 megabyte per second. And in actual, if you do very small transfer, then the transfer rates we get are 0.66 megabyte per second and 0.31 megabyte per second. Okay, this is because the transfer time for small transfer is negligible and the I/O time is dominated by mechanical movements. So this is the behavior or performance of these hard disks on workloads which do very small transfers to and from the hard disk. Okay, so the average transfer rate will be very, very low on small transfers. If you have very large transfers, let's say a transfer of 100 MB, then we'll see that the TIO for Cheetah is 100 milliseconds and the time for IO for Barracuda is 950 milliseconds, okay, based on the same calculation that you've done on the last time. T-seek and T-rotate will remain the same, only T-transfer will change because we will basically be transferring a large amount of data. Okay, so this size divided by the transfer rate will give us T-transfer. So For this kind of very large sequential I/O, the transfer rate or the I/O rate basically reaches close to the max transfer rate. This was the max transfer rate cited by the hard disk manufacturers, but you will achieve this performance only in very large transfers in which seek time and rotate time are negligible and they are completely dominated by the transfer time. Okay? So in that case, we'll reach the peak performance. Okay? But many systems are usually not making this big transfers all the time. So it is rare for systems to achieve these peak performances. Usually we will have much less performance compared to these peak performances, especially if we are doing very small transfers where seek and rotate delays completely dominate our transfer time. So this gives you some example or some insight into the numbers provided on the back of the hard disk and how they are compared to actual performance of the hard disk on your typical workloads. Okay, so we consider two types of workloads in which one in which we are doing very small transfers on the hard disk and the other where we are doing very big transfer, very large transfers on the hard disk. We see that on workloads with two very small transfers, the hard disk performance is very, very low and they are far from the maximum transfer rate that we are given on the back of the hard disk. So performance depends only on performance depends heavily on the type of workload or which kind of transfer we are doing. So when the operating system requests the hard disk to perform an I/O, whether read or write, then there are many processes running on the system or on the operating system at any given time, and all of them or many of them might be requesting different kind of operations on the hard disk simultaneously. So the hard disk may receive multiple requests, read and write requests to different locations or different sectors on the hard disk concurrently. So when we have like this multiple requests arriving simultaneously, then just like the operating system has to do scheduling of the processes, similarly, the hard disk can get to do scheduling of all these requests, I/O requests, so that on average we have an optimal performance. Okay, so when we have multiple requests of varying characteristics arriving to read or write from different locations of the hard disk, how can we sequence them or schedule them so that our hard disk performs most efficiently? Okay? So the disk scheduler, what it's trying to do is it is trying to reduce the average delay. Okay, so delay is like from a time that hard disk was the request was sent to the time that hard disk request was completed. Okay, so the difference between this request send time and the completion time, we call it a delay. And what the hard disk or the disk scheduler tries to do is it basically tries to reduce the average delay of the system. Okay. So in number of scheduling OS processes, we had discussed that the length of the job is not known in advance. We don't know, or the operating system does not know for how long a process will run. But here on the hard disk, when we request an I/O request, when we receive an I/O request, we basically can look at the size of the I/O request and basically can guess how long this job will take. Okay, so the length of the job or the time it will take to do that job can be roughly calculated by looking at the size of the job and from where it will be read or written on the hard disk. So this kind of information is available on the hard disk. So just like the operating system, we have this strategy where we try to schedule the shortest job first to reduce the average delay. Similarly, we'll try to approximate the same strategy on the hard disk, okay, to reduce the average delay. So shortest basically job first can be approximated by this strategy in which we have like shortest seek time first. Okay, seek time is one of the major delays in the hard disk. Okay? So whichever job will have the shortest seek time, we can say roughly that that job will be the shortest job to do. Okay, so shortest job first can be approximated by shortest seek time first. And seek time basically is a low level information which is available on the hard disk but is not available to the operating system. Okay, operating system, as we discussed, views the hard disk not in terms of sectors but in terms of blocks. Okay, it views the hard disk as a continuous array of blocks. So at the operating system level, the shortest seek time first can be approximated by nearest block first. Okay, because the block which is nearest will roughly speaking need the shortest seek time. So this kind of strategies can be applied when we have a series of requests to reduce the average delay of the system. But just like we can have starvation in process scheduling, similarly we can have this starvation in disk scheduling. Okay, so let's say we have a strategy which is employing this shortest seek time first or nearest block first strategy to reduce the average delay, and our head is positioned at a certain sector on a certain track, and we have different requests which have arrived and which are at different locations on the hard disk. Okay? So some of these requests are to the sectors which are near to the current sector where the head is, and some of these requests are to sectors which are very far away in terms of seek time and rotate time. So what will happen is, based on this strategy, we will first serve those requests which are to the sectors which are nearby, near the head. Okay? So we'll start servicing those requests, and while we are servicing those requests, new requests may arrive which are also to the sectors which are near to the current position of the head. So they will also get priority on the requests which are to the far away sectors. Okay, and while we are servicing those sector requests, new requests may arrive which will also be to the nearest sectors. Okay, so this way requests to the nearest sectors may continue to arrive, and what will happen is these requests that were to the far away sectors, although they have arrived very early and they have been waiting for a long time, there is a risk of starvation that if requests to nearby sectors continue arriving, then the turn of these far away sector requests may never come. Okay, and they may starve for disk access. Okay? So there is a risk of starvation in this simple strategy which we call shortest seek time first or nearest block first. Okay? So how can we come up with a method which is like reduces the delay but also does not suffer from this risk of starvation? So this is another implementation of the same strategy but in a slightly different way. This algorithm is called scan. Okay, and it basically tries to serve the nearest sectors first, but at the same time eliminating the risk of starvation. Okay? So the head basically it moves in a sweep from inner to outer tracks. Okay? So what it will do is it will basically serve the nearby sectors on this track, and then it will move to the next track. Okay, serve some sectors here, nearby sectors here, and once they are finished, it will move to the outer track. Okay, meanwhile, if there are requests that comes which are on the inner track, let's say the head has moved to the middle track, and meanwhile there are requests that have come to this inner track, which accesses inner track and which are very near to this head position. Their seek time is very low, but since the head has started its outside movement, it will continue to move outside. Okay, and these requests they will be served later. Okay, so in this way, the head basically starts a sweep from inner tracks to outer tracks. It will continue serving different requests, and if there are requests that come later and are to the inner tracks, even though their seek time is very, very low, the head will still continue to move outside. Okay, and these next requests that came and which were to the inner tracks, they will be serviced on the next sweep when the head will move back from outer to inner tracks. Okay, so this way, this head will continue, repeat its movement from inner to outer, and then outer to inner, then inner to outer, and then outer to inner, then inner to outer, and outer to inner. So it will visit all the tracks. Okay, so ultimately, all the requests that have arrived will get served, even those requests that were to the far away sectors. When the basically head will arrive on their sector track, on their track, they will also get served. Okay, requests that were to a nearby sector but came later will be served later on the inward sweep. Okay, and vice versa. So this scan algorithm has different variation, F scan, C scan, and this is sometimes also called the elevator algorithm. Okay, because elevator also, it serves different floors in a building. And let's say if you were at a top floor and you wanted to go to the ground floor, you press the button to go to the ground floor, and in between you pass to different floors, and people basically come and go and climb the elevator on those floors, and some of those, they wanted to go to the nearby floor, which is just one floor up. But since the elevator has come down, it will first finish its downward sweep, go until the ground floor, and basically serve the person who wanted to go one floor up on the next sweep, when it will go from ground floor to the top floor. Okay, so if the elevator had also employed the shortest seek time first strategy or the nearest floor first strategy, then you who wanted to go to the farthest floor, the ground floor, you would have suffered, because people continuously get on and get off from the elevator, and the elevator might have continued to move up and down, serving the nearest floors first, and your term would never had come. Okay, so the elevator also employs the same strategy to prevent starvation. Now, the shortest seek time first, as you can see from the name of the algorithm, it takes into account the seek time of the hard disk. Okay, but seek time is only one of the mechanical delays. The other mechanical delay is the rotation time. Okay, so seek time, SSTF or shortest seek time first does not take into account the rotational delay of the hard disk. Okay, so we need some other algorithm if we want to take into account the rotational delay. So for that, an algorithm that takes into account both the seek time as well as the rotation time is called shortest positioning time first. Okay, because positioning includes this seek time as well as rotate time to position the head on the right sector. Okay, so positioning time is basically a combination of seek time as well as rotate time. So again, this is another algorithm which, if you have the information about seek time, rotate time, can schedule the requests in terms of their positioning delay. Okay. So let's say if we have this head on sector number 30, and you have two requests that are asking you to read or write data, one from read number sector number 16 and other from sector number 8. Okay. So how would you decide for which sector the positioning time is lower, so that you can schedule the request with the shortest positioning time first? Okay. So since this positioning time involves seek time as well as rotate time, so you have to see which of these two times is greater. Okay, because here on line number for sector number 8, we have a larger seek time but lower rotation time. Okay, but For sector number 16, we have a smaller seek time, but a large rotation time, okay, because 16 it will take large time to rotate from here to here. Okay, so again you have to see relative to each other the seek time and the rotation time, which of them is greater, and based on that you will do that calculation and decide whether the next shortest positioning time is to sector number 8 or to sector number 16. Okay, and based on that you will schedule one of those two requests first. It's the same thing that SSTF and scan do not take into account rotation time. Okay. SPTF, shortest position time first, takes into account both seek time as well as rotation time. Okay, but the thing is, these seek time and rotate time, etc., are internal details to the hard disk, hardware level details. Usually, the operating system has a higher level overview and it does not have enough information to do or do calculations about seek time and rotate time. Okay, remember the internal details are known inside the device or maximum at the driver level, but not at the upper higher level of the OS. So where does this scheduling of requests is performed? Okay, this scheduling of requests, is it performed at the higher level, OS level, or is it performed at the lower level inside the hard disk at the disk controller level? Okay. So the answer is it can be done in both ways. Okay. So OS can do some initial scheduling based on the information that it has and then send those requests to the hard disk. And once the hard disk receives those requests, then the hard disk can basically uh, rearrange those requests, because hard disk internally has much more information about the requests than compared to the OS. So let's say the OS sends these requests in this order. Okay. The first request is to sector number 33, and then sector number 8 next request, and then sector number 34 on the next request. So the OS did not had information about the arrangement of these sectors, but when these requests arrive inside the hard disk knows that sector number 33 is much more closer to sector number 34 than compared to sector number 8. Okay, so internally it can rearrange these requests so that request number 30 this to sector number 33 is performed, and then after that the next request to be executed is to this sector number 34. Okay, because this way we will avoid the seek and rotate time, which we will have to do if we execute this request to sector number 8 the next. Okay, because first we have to go to sector number 8, and then from sector number 8 we'll have to come back to sector number 34. Okay, and again rotational and seek delays are much larger in hard disks. So therefore the hard disk, since it knows its geometry and knows that sector 33 is much closer to 34, it can rearrange these requests so that the request to sector number 34 is performed just after sector number 33, and sector number 8 is served the third or last. Okay. Secondly, another issue is that how long the operating system should wait to issue an IO request to hard disk. Okay, so it is good if the operating system can collect some requests together and send them together to the hard disk, because when the hard disk request gets these requests together, it can do some rearrangement within that list of requests. Okay. So the question is how long the operating system should wait before sending the request to the disk. Should it wait for like a fixed number of seconds, 10 milliseconds, 20 milliseconds, or should it wait for a fixed number of IO requests to accumulate, like a dozen requests or 20 requests, before it can forward the list of requests to the hard disk. Okay. So as you can guess, in this situation there is no easy or clear-cut answer, and that would depend from system to system. Okay, so different operating systems or different computer systems can have different delays for issuing hard requests to the hard disk. So this is again different strategies that you can apply immediately or after some time. Okay. So after some time, the advantage is that the OS requests multiple, the hard disk receives multiple requests together, and it can rearrange these requests. So this is the end of this chapter, in which we have studied how does a hard disk function internally. Okay, so next chapter we will basically skip a couple of chapters and then go directly to file system implementation to see how file system is implemented inside the OS. Okay, because now we know the working of the hard disk. So I'll stop this video here, and you guys can ask any questions you have in the interactive sessions. Thank you very much.